adder, the full adder. Spoke about other things, the decoders, the encoders, and we reached somewhere to code converters. Let me zoom this one. Okay, let me take the pen also. Okay, so we are trying to just finalize this chapter and have a tutorial next to it. We spoke about the encoders not last week, the week before it. Last week we had the midterm. Today we'll be starting with code converters. Code converters are actually devices, or of course the electronic or digital devices in this case, are meant to convert or exchange a code we provide to binary. And the code we provide here is in most cases are relevant to binary. Means what? In BCD, for example, binary coded decimal. It's a binary code, yes, but it has another meaning. It's not like just normal plain binary representation of decimal numbers or any other numbers. It's another type of representation, yet we can have a converter to convert a BCD or binary coded decimal code or a number to a binary code or a number. All right. How do we do it, or how actually does the computer do it? In basic sense, what we do, we check the weights. This is how it is done. Now for BCD, we represent the 10 digits that we have in the decimal system, 0 to 9. We represent them by 4 digits. And there was a question in your midterm about it, the invalid codes of BCD. Or actually, I didn't say BCD, I said 8421. It's the same. There is no change. The same name, an alternative name for BCD. So we use the weights. These weights will help us to get back to the binary. And based on these weights, we can sum up the available weights in binary and get the representation either by binary or maybe by decimal, if we are looking for that. Exactly like the way we did manually. The computer does it, but in a more automated way. Now look at this. This is a simple example. Look at this binary coded decimal code. Remember that there are invalid codes, but up until 9 inclusive, we can have it from 0000 to 1001. That's possible. That means from 0 to 9. So we have here these 2 digits. Digits I refer to the decimal representation of the 8 digits of BCD. If you have a BCD represented by 8 digits, then you have to make sure that you have, or the alternative, or the if you are going to convert it to decimal, that you will have a number of 2 digits in decimal. And this number will arrange these digits as the normal count that we have, the normal representation of decimal numbers that we have. This one could be 0, or 1, or 2, or 3 until 9. And the same goes to this one. It could be 0, 1, 2, 3 until 9. But it can't be more than 1 digit in decimal. So it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Not more than that. The same goes here. So now, how do we convert? Now look at these weights. Do you remember 8421? This is what we refer to by the binary coded decimal, the 8421 system. And these are the weights. What do we mean by 8421? We can compose any number from the BCD based on these weights. 2 to 0, 2 to 1, 2 to 2, 2 to 3. These weights. So let's say 9, that is 8 plus 1. 2 to 3 plus 2 to 1, 2 to 0, I'm sorry. Okay, let's say, take another one, 5. That is 2 to 2 plus 2 to 0, 4 plus 1, and so on. The same thing goes to what? To this part. This part, the only thing is like we have a shift in the weight. Shift in the weight means what? This is in the units. Units, that means we don't have any 0 added to it. If we speak about decimal. Here we speak about decimal. But when we go to tens, that means it is multiplied. The digit is multiplied by 10. Instead of saying 1 for this, we say it is 10. Instead of saying 20, we say Instead of saying 2, we say 20. Instead of saying 4, we say 40 and 80. So initially we said 8421. That is for the first 4 digits, that they compose the first digit of the decimal number. If we have another one, we have to multiply by 10. Then we go for tens. Tens, the same weights, 10, 20, 40, 80. If you have another one here, x, 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 okay, then what we will be having, again, another weight shift. It will be 100, 200, 400, 800, and you sum up. What does it mean? How do I know? Now look, this one, these are 4, then they represent only 1 digit, as we explained before about the BCD. All right, there is no any multiplication by 10, there is no shift in the weight, it is just the minimum weight of units here in this case. If we convert it, 1, 1, 1, 1, look at the weights. So here we have the weight of 4 plus the weight of 2 plus the weight of 1 here. So these weights, 4 plus 2 plus 1, that means 2 to 0, 2 to 1, 2 to 2. Sum them up, which is 7. We don't have any weight for 8, 2 to 3, there is no, it's cancelled, that's 7. Do the same here. Here we don't have 1, 2, 4, 8, we have 10, 20, 40, 80. So what we have here is 10, 20, 40, 80. Look at the digits that we don't have for 10, we don't have for 20, we don't have for 40, we just have for 80. So this only 1 here we have. The weight is coincided with 80. Just 80, it corresponds with 80, so that is 8. Of course, when you combine 7 with it, that will be 87. Of course, this is another code of decimal. It's not exactly the decimal type that we are using for normal circumstances, but this will work. Why? Because we are just converting between a binary coded decimal, BCD, to binary or to decimal, or vice versa, it depends. So if this is BCD, well, we can get the decimal number from it based on these weights. Okay, this is how the computer does it and how we human beings are also doing it. Now look at the conversion between BCD and binary. Why? BCD is a special type of binary. It's not just the binary that we have all possible codes. We have invalid codes in BCD. Why? Because you said we are converting the 10 digits that we have of the decimal to 4 binary digits. Then in that case, we have from 0 to 1, 0, 0, 1. Then we have another 6 invalid digits. And in that case, we are missing some part of binary. Now, if you want to convert between BCD and binary, this is like the representation in a table. It's extremely easy, actually. 1 is same in both cases. 2 also is same. Well, 3, 4. Now, we don't have for the binary coded decimal. Rather, we have 4 and 8. 3 is composed of 2 plus 1. For example, 5 is composed of 4 plus 1, and so on. Then we don't have 9, as I said, 8 plus 1. We have then 10, the shift in the weight of 1, that's 10, shift in the weight of 2, that's 20, and so on. So you look at those. For example, 80 is composed of 64 in binary representation. 64, the weight of 64. 64 is 2 to 6. So 0, 1, 2, 3, 4, 5, 6, 2 to 6. The 64 plus 16, that's 80. So look at this here. 64, we will have 1 year, and 16, we will have 1 year. That's the representation. How do I know that this is correct? This is the representation, as I said. This is the BCD weight, and based on it, we can get the weight of the binary. 80 is composed of what? 64 plus 16, nothing else. How about 40 is composed of 32 plus 8. Okay. The rest are zeros. Take 20, that's 16 plus 4. 16 plus 4. Take 10, that's 8 plus 2, and so on. You carry on like that. Now, sometimes I usually receive these questions, how can you make it this much quick? This needs training. It's not difficult, actually. It just needs training. To remember these weights, train yourself from 1 to 4, 8, 16, 32, 64. Usually we don't even double 64. We don't go to 128. It's limited to those. So they are not really hard to get the combination of those. Let's move on. All right. We have other types of codes. For example, binary to gray, gray to binary. We explained about the gray code. The gray code, the main characteristic of the gray code is representing minimum movement of bits or change of bits between numbers. Means if I want to move from one digit to another, I have a minimum change in the bits. Only one bit will change. But for normal binary, it's not like that. Think about the change of 3, which is 0. Let's take just 4 bits. 0, 0, 1, 1. That's 3 in decimal. Yes, as a binary, 3 in decimal. 0, 0, 1, 1. If you move from 3 to 4, 4 is 0, 1, 0, 0. How many bits changed in this case? 3 bits changed. That's a problem in many applications in digital electronics. And what we need to do, we need to make up for that. So they invented the gray code. The gray code, only 1 bit changes between the digits. If you move between the decimal 3 and the decimal 4, only in gray code, only 1 bit will change. Now, how can I convert between binary and gray, or from binary to gray? It is extremely easy. If you start from the MSB, the most significant bit, it is the same for both binary and gray, the same. The bit is the same. So if you have a binary bit, binary number, let's say 1010, okay. Let's say just a simple representation. Or these are 4 exactly. So this is the MSB here, okay? You keep it the way it is, 1. That's also the MSB of the gray, 1, the way it is. We need to XOR the MSB with the digit next to it. So we need to apply XOR here. XOR, if they are different, then the output is 1. If they are same, then the output is 0. Now, 1 XOR 0, that's 1. Now here we have 0. Why? The number is 10, 10. Here we have 0. So 1 XOR 0, that's 1. Good. How about this one? This one we have here 1. Then the last one we have 0 is given. Here I gave it 10, 10. It's just an example. Okay. 10, 10. This is 0. I'm sorry. 0. 10, 10. Okay. So here in this case, we got the second next to the MSB. We need to get the next to that 0x or 1. Here we have B2x. That is 0x or 1. That's 1. Okay. 1x or 0 is also 1. Now this is well, by chance it's all ones, but it may not be the case. It depends on the application, but this is how we do it. How about the other way around, converting between gray to binary? So if you want to change the gray or convert the gray code that you have to binary, you apply the same concept. You start from the most significant bit. So we have, again, let's try to convert this one back. I have 1 here. Okay, that's the MSB here. It's the same. We apply nothing to it. Now, in order for us to get the output, the next output, we take the next gray code, the next to the MSB, the next bit, I meant. So 1 XOR 1, we XOR it with the MSB. the next to the MSB, the bit next to the MSB, okay, or the right before the MSB, we XOR it with the MSB. 1 XOR 1 is 0. Okay, this one will be XORed with the next. Now look, I have a feedback from the output. So 0 will be XORed with 1, here, this one here, okay. 0 XOR 1, that's 1. 1 will be XORed with the last one, here, this one. 1 XOR 1, that would be 0. We get back to 1 0 1 0, the one we assumed here. This is the MSB, this is the SB. This is the way we convert it. Okay, these are also other applications. If we have a binary 0 1 0 1, another way around. The highest or the most significant bit will be the same, then XOR the next. 0 XOR 1, that's 1. 1 XOR 0, that's 1. 0 XOR 1, that's 1. So it would be 0 1 1 1. If you want to do it the way around, like convert it back again, apply this. The MSB will be the same, then XOR the output of XORing the MSB and the bit before it, and you will see the output, how it goes. All right. So let's move a bit. Multiplexers, these are extremely important. Let me check if everything is okay. Guys, can you hear me? Let me check, because I can't hear you. Can you hear? Is there any problem? Can you see? Can you hear? Give a feedback. Okay, good. All right. Okay, let's go to multiplexers again. All right, good. Okay, I got your feedback. So for multiplexers or MUX, multiplexer, we refer to it by MUX, MUX, okay, a multiplexer. Multiplexer is a device actually that takes different input data from different, you can say, inputs and gathers them or combines them to one output. This is the simplest way. And since we are speaking about logic circuits, we speak about only multiplexers for digital data. We don't speak about analog here. So we have more than one input, and we need to get it, or we need to combine them to one output, so we need to have selectors, or a way to select, okay? And that's why we refer to multiplexers by data selectors. There is another name for multiplexers. It's exactly like data based on some inputs or some data selectors, okay? Now look at the representation of a MUX. A MUX can be represented exactly like this. We have this square or rectangle here, if you like. It has the MUX, the MUX name, and then we have data select. Data select will be 2 bits for 4. If you are just selecting between 2 data, like 2 inputs, in that case you can have 1 bit for selector. Usually that's not the case. We don't have only MUX for just 2 inputs. Usually not. We don't have that. But this is a standard. This is a standard MUX that we can have 2 selectors. Selectors. How many choices do we have? 2 to 2. 2 to 2 is equal to 4. So I can select 1 out of 4 each time from data. That's why we have 4 data bits here, D0, D1, D2, D3. So we have the selector 1 and 0, or selector 0 and selector 1, and based on the values set here, we can choose, or we can select D0, D1, D2, D3. So maybe you are asking yourself and telling now, select for what? We have different inputs. We need to combine them only to one output. So there is only one way to do it now. All these selections, and that's how the multiplexer does it. And there are many applications for multiplexers based on this theory. Look at the selectors. 0, 0. Pay attention to the arrangement. S1 is 0. Okay, 0, 0, 0, 1, 1, 0, 1, 1. So we assume that this has a lower weight. This is the higher weight. Okay. Now, 0, 0 takes us to D0 in the output, or allows D0 to be displayed or passed to the output while it will make the rest of the inputs cancelled or zeros, or they do not have any effect. So if we have 0, 0 as data select, then D0 will be out. If we have 0, 1, 0, then we will have D2. If we have 1, 1, we will have D3. Now it depends on you, how you arrange these D0, D1, D2, D3, how you arrange them as inputs. This is the input with like 0, 1, 2, 3, like you mark them as the first input, second input, third input, and fourth input, because we have 4 data inputs. Now it depends. You may put D3 here. It depends. It doesn't matter. It wouldn't change that D3 in that case would be selected when S1 and S0 are 0, 0, like this. All right. So based on the selector, we will product of some terms. What does it mean? It's exactly Y here in this case equals to what? Now we have the choice S0, S1, S0, S1. S0, S1, actually, it's actually not a big deal. It doesn't matter, their arrangement, not exactly a big deal now. All right, now in this case, bar, bar, not S1, not S0, then that's also ended with what? With D0. Okay, or next, you go to the next term. S1 bar, S0. It's like what we did before. One bar, S0, or D1, and D1. And you keep ORing all these terminologies. I can show you here. This is easier and nicer. Like 0, 0, that is D0, S1 bar, S0 bar, or not S1, not S2. Then we OR all of them like this. The selection when both of them are complemented, that means 0, 0 here, 0, 1 here, 1, 0 here, 1, 1. Exactly what we did in the design based on the truth table. All right. This is the representation in basic gates, like if we use AND and OR gates. Now look at this. So what we have, you can apply, we have NOT gate. Oh, we have S1 and S2 both inverted and non-inverted, complemented and non-complemented, uncomplemented. So we can apply the inversion here. We need S0 and S1, and then we need the data. So the selection here will activate an AND gate or will actually deactivate it. It depends. Why? An AND gate will be active if all inputs are ones. Now for the selectors, we can guarantee they are ones, but we don't know about the data. So it doesn't matter. Why? If the data is 1 and the selection is actually activating its gate here, then it will be displayed at the output as 1. If it is 0 and the selectors are also activating the gate here, it will appear as 0. Why? Because in that case, what we are looking for here is ultimately the value of the data. If it is 0, it will come out as 0. If it is 1, it will come out as 1 if the gate is activated. If the gate is not activated, then we are just having a 0, which doesn't change anything in OR gate. We are ORing, so 0 wouldn't change anything in OR gate. Exactly as 1 wouldn't change in an AND gate. All right, so this is the design. These are the selectors. So we select, let's say, I will explain this one only. D0, we need to activate this AND gate based on not S1, not S0. So we take the inversion of S0, we take the inversion of S1, and we pass D0. If you move to D1, now remember, for D1, we have 0, 1. So the inversion of S1 is taken to D1, and then S0 the way it is. You keep on moving according to those exactly like this. Before I brought this one as an exam question, I just needed the output, and the questions or the answers were amazing, as you know. So this is one type of the questions that we usually ask. We may give a waveform. Means what? I give you this kind of data selector, okay? And I give you the data selection here, data select, those as inputs by wave. So we have these wave given, and we have the data also as waveforms. And what we need to do, we need to get the output Y. Now, in order for you to do it or to solve it in the easiest way, as easy as possible, first mark S0 and S1, or S1 and S0. So S1 and S0 are given. Look at those. Low and low, 0 and 0. When they are 0 and 0, then what are we going to select here? That is D0. So the output, you don't have to care about D1, D2, D3. You don't have to. You ignore them. Just disregard all of them. Look at D0. Since S1 and S0 are zeros, then all you need to look at is just D0. Okay, what is D0? That's a 0. This would be the output for the first time. I can just write it, not draw it. It's easier. 0. Okay, so this is the case. And then what we can do is we can apply the same, move next to the next selection. Look at the next selection, S1 and S0, 0, 1. That will activate the second gate, gate for D1. So you disregard this one, gate 0 here. You disregard. Guys, I have to take this phone. Wait a minute. Efendim. Ben meşgulum. Sonra ara. Okay. Sorry about the phone. So, where were we? We got back. All right. So, next to that, take this stage here. Take this one. 1, 0. 1, 0 will activate the third gate. Okay. Will activate the third gate. So in that case, what will happen? We will cancel this one, we will cancel this one, and this one. Only this gate will be, so we are taking D2. What's available? I forgot to pass this one, the phone call disturbed me, sorry. Here what we have is, we have 0, 1, we said earlier, so D2 will be, sorry, D1 will be out. So D1 is 1, we will have 1 here. Then 1, 0, we will have D2, that's 0. Then we have 1, 1, that will take D3. So D3 is what here? 0. Move on. 0, 0. Again, that will take D0, that's 1. D0 here is 1. Then 0, 1. That will take D1, that's 0. Okay, 1, 0, that will take D2, that's 0. Okay. And 1, 1 will take D3, that's 1. And that's it. As easy as it is, okay? As easy as it is. Okay, these are the values, these are the data bits, the bits that we have, as I explained earlier, the selections. So you will get D0, D1, D2, depends on the selectors. The rest of the Ds, if one of them is out, the rest of them are disabled, or they will not be displayed, they will not be given as an output. All right, let's move next. Multiplexers, we have also standard multiplexers for 8 bits. They take from D0 to D7, 8 bits as input. they will get you these inputs all on one line, okay, all on one line. So the idea here is to have selectors accommodating these 8 bits. So 8 is equal to 2 to 3. 2 to 3 in this case will accommodate 8 bits. So we need 3 selectors. So we have S0, S1, S2. We have these selectors, and these selectors will allow us to choose or to select between the data inputs. The same concept applies to this. What we just did here is the same, but we have only one extra selector that will allow for double the size of 4 before. Now we have 8. If you have 4 selectors, you'll have 16, but this is the standard. We refer to this one by G0/7. That means we select from 8 inputs from gate 0, or from input 0 here in this case to 7, and in that case we will get Y. One more thing, we have 2 outputs. One of them is Y and the other one is Y bar. Okay? All right, good. So now what are we looking for is the output of this multiplexer. One more thing, I explained about the enable. Enable is actually, you can say, is like on-off in any electronic device. You can control the whole mux by either activating or deactivating the enable. Now look at this. Enable is complemented. It means it will be activated if it is low. If I provide 0, or in other words, I ground it, grounding, in that case, the output, the output will be, the mux will be activated. Otherwise, if I apply here 1, the mux will be deactivated. It will not be activated. It will not work. Whatever you provide as selectors or data, the output will be just 0. It will not activate. The mux will not activate. All right. Let's take an example. These are the common examples. Usually we bring them in the exam. Use an 8-bit or 8-bit muxes. Muxes more than 1. So just use 8-bit. That means 8 like this. As many as you like. It depends. Okay? And the necessary logic gates to multiplex 16. Now we speak about 16, not only 8. We speak about 16 data lines onto a single data output line. Okay? So what we are looking for here is 2 muxes, 2 or 3 or more of this. Now this one accommodates 8. It's easy. If you want to multiplex 8 bits, then no problem. It's just, you can just bring this one, this standard mux. But if you are looking for 16, this one is not enough. Why is not enough? This accommodates only 8. How can I make it enough for 16? Well, in order for me to make it enough for 16, I have to improvise, and the question is telling me use muxes. Maybe I can use 2 of this one, and then improvise. Improvise how? Now think about it. 16 data lines. When we think about 16 data lines, in that case, we need to have 4 selectors, right? 4 data for selections. How about if I use the 4 data for selection, the fourth one, let's say here we call them S1, sorry, S0, S1, S2. Now we need S3, okay? Because 4, 2 to 4, that's 16. S0 connected to 0, S1 connected to 1, S2 connected to 2, S3 connected to somewhere else in that case. There is no here 3. What we will do, we will connect it to enable. How? Now think about it. If you have this kind of weight, look, we have the weights like this. 1, then 2, then 4, then 8, then 16. Okay? Now, in that case, what do we have? If the number is up to 8, just 8, like this, then the weight of 16 will not be there, it will be 0. Right? Why? Because we may have 1, we may have 2, we may have 4, we may have 8, or combination of those. That's possible. But nothing will reach to 16. That's impossible. The weight of 16 will not be there. Good. So I say S0, S1, S2 are connected to their normal gates. S3, I connected to enable bar. If the number is less than or equal to 8, 4, 2, 1 in this range, it will accommodate D0 to D7. Okay? It will enable the first mux. I will take its inversion, the inversion of S3, I'll connect it to the enable bar of another mux. And then pass D8, D9, D10, D11, 13, 14, and so on. Okay? That's exactly how I do it. Now look at this. This one will be easier. Now this. S0, S1, S2 are fine. They will be connected to their own gates, but S3 will enable the mux if it is 0, low. So it will accommodate D0, D1, D2, D3, 4, 5, 6, 7. We can't go more than 7. Why? These are the weights 8, 4, 2, 1. Here. If the weight is going more than this, then we can accommodate another 1. So look, if this one is active, S3 is 0, then this one is active. If S3 is 0, then this is 1, and this one will be inactive. If S3 is 1, then this one will be deactivated, and this one will be activated. So we will move all here, we will move to 0, the output here is 0, we will have outputs here. So we will accommodate for D8, 9 until 15, another type. Then what we need to do, we need to OR the two outputs from these multiplexers. Now this is the negative OR. Negative OR, why? Remember that we have the inverted output here. So if we take the negative OR, we can get back the output in its normal form, in its normal augmented form. All right. So this is the idea. We can use the multiplexer in another form, in another way, logic function generator. A function that, a generator that creates like different types of function. It's actually extremely useful to use the multiplexer for generating functions. Functions in that case based on the data selection, the selectors that we have. In that case, we can apply the selection to produce the sum of products. And that's a function generator. How do we do it? Now take this example. This is a direct example, and it's actually straightforward and easy. Now, let's say what we are looking for. Implement the logic function specified in the table below using an 8 input data selector multiplexer. Now, in order for us to do that for OR gate or whatever sum of OR product or product of sum, we can do that easily. We can take the output Y, mark 1 or mark zeros, and then get the product of sum or sum of product, and then we get the output. But now, no. What's requested is to design this one using multiplexer. All right. Now we have 3 inputs. A0, A1, A2, we can use them in the selector, and then we have 8, 2 to 3, that is 8 input data. Then we will design the output based on our data and the selectors. Now these selectors are given exactly like the normal rhythm that we know, 0, 0, 0, 0, then 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, etc. Okay, so what we are looking for here is the output. The output here is simply represented based on values of 0, 1, whatever we are given based on certain rhythm selection. Now we have only two choices, 0 and 1. Of course, this is binary. So 0 and 1 can be accommodated by either 5 volt or actually high. We can refer to it high. Okay. And that's it. And 0. 0 is ground. Okay. So this is 5 volt and ground. Okay. Now, what we are looking for here is multiplexing. Multiplexing what? Based on these states. Now look at Y. When all of them are zeros, then the output is 0. Good. So when all of them are zeros, then D0 will be out. This one. Okay. D0 is out. So what are we going to do? It's connected to 0. Why the output is 0? Connected to 0. Connected to 0. Good. Look at the second state. 0, 0, 1, that means the second gate. Gate number 1. Or input, sorry, and not gate, input. The output here is 1. So we connect it to 5 volt. Okay, next 0. That's 0, 1, 0, the third input. That's also 0, connected to 0 volt, the ground. Next to it, 1. So gate 3 connected to 5 volt. Okay. The next one 0 connected to 0. The next one 1 connected to 5. The next one 1 connected to 5. 0. So what you need to do is mark all ones, connect them to 5 volt based on their own inputs. The rest connect them to zeros. Okay. Good. All right. So that's the idea. This just basic idea. Now in the output, you don't add those. Zeros, that means cancel them. Why we put D0? Because we don't know if it is 1 or 0. But if it is 0, we are sure, then you just cancel it. Anything ended with 0 is just 0. You just remove it. You don't regard it. So you take those. It means what? A2 bar, A1 bar, A0, and Y. Or Y in this case is 1. I hope there is no problem. Let me check. Seems there is. Is there any problem? Well, if you are going to leave, no problem. That's fine. You can go. That's fine. That's totally fine if you would like to go. No problem. Okay. For those who are asking permission to go to the other class, you can go. No problem. All right. Okay. So let's go back to our explanation here. What we have is this kind of representation. When it is high, 1 connected to 5 volt. When it is low, connected to 0. And what we have as Y here, you don't have to put 1 and the output Y. 1 ending with 1 is nothing. Actually, it's like will not change anything, so you put only the selections here. So this is the way. Let's take another example. This example is a bit more advanced, and it's actually not hard. I'm sorry, it's not hard. Let me take the pen. What's requested here? Implement the logic in the table on right by using 8 input data selector multiplexer. So we need only 1. It's restricted. Now look, we have 16, so we have 4 selectors. Earlier, the question here told us we could use this one. We could use more than 1 mux. Here this question is telling no. You can just use only 1. But we have 4 to select from. How can we do it? Now it's easy. Earlier we used A3 to accommodate for some change. Now maybe we can look for the same purpose, but A3 is changing based on these 8 here. That is not good enough. It will be disturbing if you use A3. How about if I use A0? That's much easier. Why? It changes like bit directly from one field to another. Means what? 0, 1, 0, 1, 0, 1, 0, 1. So it changes continuously based on the state available. So if it is 0 now, it will be 1 next. If it's 0, 1 now, 1 next. So I take A and not A for accommodation. Earlier, well, this one could be for many states. That means 8 states, another 8 states. So I keep A0 for accommodating for that loss of more than 8, than 16-bit. I can use A3 to accommodate 8-bit, that's fine. 2 to 3, that is 2 to power 3, that's 8. Okay, good. How about the output? Now we said about the output earlier, 0 and 1, that's okay, but now we have a bit of a change. Bit of a change means what? If I cancel A0, then I'm not going to take this state and this one as separate. No. These two states, 0 and 1, will be one state. Why? Because the change of A0 is cancelled. We're looking for two cases at the same time. So these two will be 0, state 0. These two will be state 1. These two will be state 2. And so on until we reach to these two will be state 7. Okay? Why? We cancel the A0. Okay, how do I solve this issue? It's easy. Now look at this. Watch this. 0, 0, 0, 0, 0, 0. These are not changeable. The only changeable is A0. That's one state, state 0. Good. How about the output? Now look at Y. For Y, 0, 1, it follows exactly A0. Look, 0, 1, also the output Y is 0, 1. It follows it. How about if we apply A to D0, the first input? Okay, that will do. Why it will be exactly D0, why this is the choice here. A0, sorry, A3, A2, A1 would be the selectors. When they are all zeros, they will get me D0, so I apply A0 to that D0. Okay, how I get the output Y? Good. So I solve the first state or the first input. Let's take the second input, which is number 1, 0, 1. That means this is second input. Look at this. These two states, 0, 0, 1, 0, 0, 1. So look at the change here, 0, 1 again, the same. Look at Y. Y, the output is the inversion of A0. When A0 is 0, the output Y is 1. When A0 is 1, the output Y is 0. So it's the inversion of A0. So I connect not A0 to D1. Good. Let's move next. How about 4 and 5? 4 and 5, again, I check, I watch. 0, 1 here, also 0, 1. Connect directly to A1. How about 6 and 7? 6 and 7, look at here. 0, 1, then 1, 1. Okay, we have continuous ones. Then you connect 1, 3, connect it to 5 volt. It doesn't matter. The value of A0 doesn't matter. That means I take high always. Okay? Then take the next 6 and 7. We said, sorry, 6 and 7. Then with 8 and 9. That's 4. Okay? 8 and 9. Now look. 0, 1. Again, 1, 0. So the inversion of A0. 10 and 11, look at 0, 1, 1, 0. Also, again, the inversion of this. 12 and 13, 12 and 13, 1, 1, again, 5 volt. Okay? How about 14 and 15? 0, 1, again, A0 with no inversion. Same. 0, 1, 0, 1. Okay? So this is the case. This is how we do it. Now, if you look at this, A0. Now, A1, A2, A3 are fine. You connect them to their gates. A0, you connect it based on what we said earlier. The first, it's connected with no inversion to 0, then with inversion to 1, with inversion to 4, with inversion to 5. Then it's also connected with no inversion to 2 and to 7. Then the 5 volt is connected to 3 and 6. And that's the design. This has a bit of an idea. It's not really hard, but it needs just like a little bit of a concentration. Let's think about the opposite way of multiplexers. We actually combined the inputs and we got them to an output, then what we are going to have is demultiplexer. The demultiplexer is exactly the opposite, or a device that does the opposite process of multiplexer. It's a device that receives from one line, then distributes to other different lines, gets you back the data that you combined to one line or onto one line to different lines. This is exactly the idea of demultiplexer. We refer to it by demux. Demux means a demultiplexer, and this kind of a device is actually supposed to receive one data input, then distribute over different gates. Now look at this. This is the simplest way of its representation. We have one data input, which will be distributed to all gates, and then we will have selectors, inversions, distributed to all these gates. Now it depends on the selection. Now the selection, I want to activate this one when S1 and S0 are zeros. So I take their inversions. So it means data input, or D, here it will be activated D0 when S1, S0 are complemented. Okay? So you take the complement of these two, okay? Complement of these two. All right? Good. What we need to do, the same goes to the second gate. The second gate, if this one is 0 and this one is 1, so this one is 0 means I take the complement of this, and I take the one S0 the way it is to the second gate, and so on. That will distribute back the data based on these gates upon the selection, to these gates upon the selection or based on the selection. That's how we do it. This gate will produce D0, this one will produce D1, this one will produce D2, this one will produce D3, based on these selectors. All right. We may ask the question of wave, like we give you the data in as a waveform, and we give you the S0 and S1 as inputs, like also waveforms, and in that case we ask for the output, or what are the waves of D0, D1, D2, D3. This is easy. Let me explain to you how to solve it. You have the data in. The data in will be exactly D0, D1, D2, D3 based on the selection. So the selection we have S0 and S1. Okay? So based on those, there will be the selection 0, 0. What we selected? Of course, data in, this one here, but will be given to which one? It will be given to D0 when it's 0, 0. So this one will be D0, the rest will be zeros. So D0 will be 1, all the rest will be zeros. Good. How about 0, 1? 0, 1 will be all of them zeros except D1. Okay? How about 1, 0? All of them are zeros except D2. So D2 will be what? The input data. Here will be 1 for D1. Here will be 0 for D2. Look at this. 1, 1. 1, 1 will only activate D3. What's the data? 1. It will be here. Whatever the data is, 1 will be displayed. Then, again, 0, 0 will allow you to take D0. That's 0. Then, 0, 1, again, will take D1, that's 0. 1, 0 will take also D2, that's 1. 1, 1 will take D3, that's 1, and so on. This is the way. So look, 1, then that is D1, the rest are zeros. Then that's D0, sorry, that's D1, 0, etc. Now look, the selection of D0, remember the first, here, S1 as 0, then here, 0, 0. Also here. So initially here is 1, here is 0, the rest will be default 0. Why? Because we are not selecting D0. Now look at D1. D1 is activated here. So that is 1. Before is 0. Now also activated here. That's also 0. And you move on with them like that. All right. It's possible actually to have a demultiplexer as a decoder. Decoder means what? We have 4 selectors, for example, to select between 16, let's say, to distribute, to distribute to demux from 4 to 16 gates. This is possible. And we have the enable, so the data will be supplied to the enable. Why? Data could be only 0 or 1. So it depends what you are looking for. Here is 0 or 1, and it will be activated based on the selection, just the selection. And in that case, what we are going to distribute the data in will either enable or disable the chip, and then the selection will get you which data output will be there. All right. I explained about the demux for this application. Let's take the last part, which is the parity generator. The parity generator, we said that when we deal with digital signals or digital quantities, we expect errors. The error is possible. We may have an error. The error is usually composed in a bit in terms of either 0 is changed to 1 or 1 is changed to 0. That's the type of an error in digital systems. There is no any other type of an error. We may have more than one error in one bit. Why this error is happening? We have different sources of error, either electrical noise or sometimes like interference from other machines, or sometimes lightning, maybe engines, noise, whatever. All these cause a problem in the alteration of one bit from 0 to 1. All right. So if we have this kind of error, how can we detect it? How can we detect that there is an error? We have something we call it parity generator and checker. Why? Because we may have to generate a parity bit to check if we have a problem in our system or not, if we have an error or not. And also we may have to need, or we may have to use a checker to check if we have a problem in our own, received bits or received quantities, okay? So now, what are we going to have is a common type of a parity generator. The common type is like this. It's based on XOR, XORing of bits. Now, if we XOR bits, remember that when they are same, the bits are same, the output is 0. When the bits are different, the output is 1. So we can create even and odd parity. Now look, based on these two, if I XOR them, the output will be 0 if they are same. That means if there are even number of 1s. So if I put here 1 and 1, then the output here will be 0. So we have even parity. This is easy to check that one. If the output is low, then we have an even parity. If the output is high, then we have an odd parity. How? Now assume that this is, okay, we said 1 and 1. Let's say 0 and 0. Again, the output is 0 in similarity, in the case of similarity. How about if we say the input is 0 and 1? Of course, could be 1 and 0 from the side, it doesn't matter. The output will be 1, not 0, okay? And in that case, we have only 1, 1. That means odd parity, odd number of 1s. You can expand the XOR. Why? Standard XOR accepts only 2 inputs. If you want to expand it, that means you take 2 bits, you XOR them, you take another 2 bits, you XOR them, then you XOR the outputs of these 2. Then you take the final output. That's possible. But other than that, we have something we call it 9-bit parity generator checker. It can be used for generating the parity bit, or it can be also used for checking the parity, checking the error, for error detection. Now look at this. We have 9 inputs from A to I. These are all inputs. Now look at the design. If we have 0, number of 1s, or 2 number of 1s, or 4 number of 1s, or 6 number of 1s, or 8 number of 1s, then we have an even parity, and the sum even will be high, and the sum odd will be low. Why? Because we speak about even parity. Even parity, we have even number of 1s. Okay, good. If we have 1, 1, 3 ones, 5 ones, 7 ones, 9 ones, we will get low in the sum even, high in the sum odd. That means we will have an odd parity output. In that case, it's odd. It will get us to odd parity. In this case, it will generate odd parity. Why? Because the inputs are producing actually an odd parity or an order of ones, okay, the inputs. That's how we do it. If you want to design a checker now, now remember, the idea is like this. When we have even number of ones, the sum even is high, okay? But how can we detect for error? Well, what we need to do is we need to use them interchangeably. So if we have even number of ones, we can check the sum odd. Sum odd, if it is low, then we have no problem. That means, in that case, we have an even number of ones as an input for the input. If you want to check for the odd parity, in that case, well, you can check for the sum odd. If it goes low, well, sum even will go high. So you inspect. The sum even will be low in that case if you are looking for the even parity, and the sum odd will be high, and vice versa for the odd parity checker. Okay. For the generator, as I said earlier, it will produce 1 for if the even parity is there with even ones, 0 for odd, and the other way around. And that's how we do it. We usually ask questions like this. We give you a waveform, and we give you the sum even and the sum odd, and we see if based on this there is an error or not. I'll give you this one as an exercise. Please check, and then we will have actually a tutorial. This is the end of the session. Let me take your questions before we end the session. Do you have any question? Do you have any inquiry? Is there any problem you couldn't understand? Any question? No? Only 3 of you? That's great. Wonderful. Guys, do you have any question? No questions? No questions? All right. Then we are going to take a break until 3 to start our tutorial. Okay. I'll see you around 3 when we start our tutorial. Until then, enjoy your time. Goodbye.